So today we're going to talk about creating a database with Cloud SQL. So that's going to be our first step, is we're going to launch Cloud SQL. Then we're going to move on to setting up Kubernetes. We're going to be using GKE to launch our cluster. And then finally, we're going to deploy an application on that, and we're going to examine the fault tolerance of the application. So we're going to take a look at what makes it resilient, some couple of ways it can crash, and how we can get it back up as quickly as possible. So my name is Kurtis Van Gent. I'm a developer programs engineer for Google. I work on Cloud SQL. So one of the things I do is try and make Cloud SQL more friendly for developers. That's pretty much my whole job. It's what I work on every day. But I want to hear a little bit about you guys. So I know we still have some people coming in the room, but I'm just going to go through each one, and let's try and get a show of hands. So how many people in here consider themselves a developer? Go ahead and raise your hand. All right, we got a ton of developers in here. That's great. So how many people consider themselves system admins? Okay, a few hands, not very many. How many of you guys consider yourselves DevOps practitioners? Okay, great, quite a few hands. And how many of yourselves consider yourselves DBAs? A few hands. How many of yourselves don't really want to consider yourselves a DBA, but you do anyway? Okay, there's like 5 or 6. Great. That's usually how these talks go. So, okay, sweet. Well, that gives us a good starting point. I'm going to try and introduce some of the terminology so that if you haven't used Kubernetes before, you'll still be able to follow along and keep up. But we are going to skip over some of the basics, like how containers work. This is a 300-level course after all. I don't want to bore everybody else too badly. So, so now for a really personal question. Do you guys use tabs or spaces? Right? So why don't we get a show of hands for tabs? Okay, there's like a little over half, a little under half maybe, a little under half. Okay, how about spaces? Okay, it's like 40% of each and 20% just don't care. So today our application is going to be talking about launching, the application we're going to be launching is going to be a voting system for tabs versus spaces. And so as you guys obviously care very deeply about this, we have some specific goals of this. We need to be able to handle high traffic. So when everybody gets on their phones, the application has to be able to respond. I don't want anybody calling, hey, voter fraud, I couldn't get my vote for spaces in, so this doesn't count. It needs low maintenance, so I'm going to be up here talking. I don't really have time to monitor it, so I need to make sure that it's taking care of itself and it doesn't really require a lot of hands-on from me. And then I need it to be almost always available. If it goes down, you guys are going to cry foul. You're going to say the results aren't fair, and we need to make sure that that doesn't happen. So with that in mind, let's take a look at what we have for our database. We're going to be starting with Cloud SQL today. So if you haven't used Cloud SQL before, there are some really great benefits to using a managed database. The first of all is you don't have to be a DBA anymore. You can just let Google take care of it. So it's fully managed. We have Postgres and MySQL instances, and you can run your instances anywhere. So you can deploy it to any region in the world that we support, and it'll work great. You also get some advantages like performance and scalability. So Cloud SQL is optimized for our VMs, so we take MySQL, we take Postgres, we tune all the flags so that it works as best as possible running on our hardware. And you can also change the size of the hardware with a few clicks of the button. So you can go from 1 instance to 64. If you write an app and it becomes popular overnight, you can scale your database up. If you are running a lot of high-volume queries, you need a little bit of extra RAM instead of a little extra CPU power so that those have enough space to optimize. Those options are all available for you. And then last but not least, you get reliability and security. So we've got 99.95 SLOs around availability, and you also get advantages like the high availability options, which we're going to talk about in a second. So high availability is one of my favorite features of Cloud SQL. Specifically for Postgres, we have a really unique way of implementing it. How it works is we have, so in GCP, if you guys aren't aware, we have regions, and then within those we have fault-tolerant zones. So zones are, an entire zone can go down, and nothing will affect all the others. They're completely separate. If you spin up a Cloud SQL instance, you start with a primary instance. You're going to click one button to enable high availability, and you're going to get a standby instance in a second region. So that's going to work using our persistent disk. That's a service we offer. It does storage-level synchronous replication. So as soon as your database writes in one zone, it automatically is synced to the next zone. The advantage of this is you don't have to worry about any replication lag or anything like that. As long as your database accepted the transaction, the backup is going to have it as well. So because of this, we have the replica waiting for you. All we have to do is say, promote that one to master. Failovers are very, very quick. Typically take less than 60 seconds. If you guys want to check it out, we have a demo on the floor today, high availability with Cloud SQL, and the averages are somewhere around 35 seconds. So connecting to Cloud SQL, when your database is in a cloud, there's always some interesting problems you have to run into. So Cloud SQL has a few different connection options. You pretty much have to choose between two different groups. You have to choose one connection path, and you have to choose a way to authenticate. So when it comes to connecting with Cloud SQL, we have public IP. So that's an IP that's open on the internet. You will have to pair it with authentication. By default, it's closed off. You can only access it if you're an approved user, and we'll go through how to do that in a second. And we also have private IP. So private networking is available if you're using our VPC technology. That allows you to create a cluster, mark it as VPC, and then all of the things inside that VPC talk directly to each other. They don't have to go outside of Google's network. Everything stays private. Everything stays secure. With authentication, you've got a couple of different options. Most of these are used with public IP, but they definitely can be used with private IP if you want that extra security. The first option is whitelisting an IP. You can create a list of IPs that are allowed to connect. This is an OK option, but if any of you guys are familiar with security, there's a few disadvantages to that, so we offer some other options as well. You can have an approved SSL certificate. So you can click a button, get an SSL certificate, distribute the client key to your application, and link up with it. Or you can use my favorite way, which is the Cloud SQL proxy. The Cloud SQL proxy has a bunch of advantages, including security, and it gives you control with an IAM account. So you can actually create an IAM account, say you're allowed to talk to this database, and then if for some reason you decide that application should no longer have access to this database, you can either remove that privilege, or you can just delete that account entirely, and they'll no longer be able to access your database, which is great. So today we're going to be using the Cloud SQL proxy to connect. So like I mentioned, it's really convenient. You don't have to worry about whitelisting. You don't have to worry about managing SSL keys. All you do is create the IAM account, apply it to a service account, and the service account will connect on behalf of your application. This makes it really quick, really secure. This proxy is also open sourced. It's available on GitHub, so if for some reason there's something with the proxy that's not working for you right, you can download the code, you can compile it yourself, make whatever edits you need to. OK, so with all that in mind, let's go ahead and go through the demo. We're going to take a second and connect to Cloud SQL. So if we could switch to the laptop. All right. So here I've got a project created for us. We're just going to open this up, go to the Cloud SQL page. I've created a backup just in case the demo gods aren't happy with me today, but we'll create a fresh one. Well, let's choose Postgres, pick an instance name, and then I'm going to use a really secure password here. All right, so you can choose any region you want. So this is the regions that we talked about earlier, and then you can pick any zone. I'm going to go ahead and specify a zone for no particular reason. In fact, we can pick any of these zones, and it's fine. You can choose your version. We just entered beta for Postgres 11, so if you guys are interested in that, you can check it out. We can set our connectivity, private IP, public IP, all of that. We can change the size, so if we decide we want a little bit bigger, we can scale that up. We can even add extra RAM if we need to. We'll keep it pretty small for right now. And let's go down to high availability. So this is the high availability feature we talked about. This is going to make sure that we always have access to our data with no involvement from me. So I'm going to go ahead and look everything over. Great. I'm going to go ahead and create that. OK, so as you can see right now, what's happening is we're spinning up the instance. It usually takes like 4 to 5 minutes to spin up a Cloud SQL instance. So it's not very long. It's a lot faster than trying to install Postgres yourself, or at least when I try to install Postgres myself. Let's go ahead and go back to the slides. So while that's going, let's move on to the next step and talk about Kubernetes. So how many people have used Kubernetes here before? Great, quite a few people. So at Google, we run everything in containers, like as much stuff as possible. Gmail, web apps, everything we can runs in a container on our infrastructure. Even Google Cloud Platform runs our VMs in containers. So whenever you spin up a compute instance, that's actually a container. And we launch several billion containers per week. Now, obviously, Google has a lot of employees, but not enough to hand manage several billion containers a week. That's a lot of Docker runs to type. So we came up with something called Kubernetes. So Kubernetes is actually based on something we have internally. It's open source, it's written in Go, and what it does is it manages fleets of containers. So what that means is that you can essentially just tell it what you want your application to look like, and Kubernetes will make it happen. It is based on our internal system, which is called Borg. We took a lot of the stuff we learned when we created Borg, and we brought it to Kubernetes. It supports multiple cloud environments. You can run this not just in GCP. You can run it on-prem. You can run it on whatever cloud you want. And it supports multiple container runtimes, so you're not locked into anything if you don't want to be. So if you aren't familiar with Kubernetes, we're going to go through just a few terms that we use. Specifically, one of them, the first is when it comes to Kubernetes, you have clusters. So a cluster is a group of nodes, and there's one master node. So the master node monitors the entire state of all the other nodes, and it updates the environment as needed. So it's going to take a look. It's going to say, hey, I'm supposed to have 3 nodes here, but I'm missing one, or something's not working, and it's going to work to correct that. So when we talk about node, we're talking about a single machine in a cluster. So we're going to spin up a cluster. It's going to have 3 nodes in it, and each node represents a VM or a different machine that we're running on. And then last but not least, we're going to talk about pods. So a pod is one or more containers. So a pod is an atomical unit in Kubernetes. What it is it's an instance of your application. So you try and make the pod as small as possible. You represent one runtime of your application. And sometimes you have multiple containers, which we'll talk about as well. So if you use Google Kubernetes Engine, there's even a few more advantages. So you have auto repair. If one of your nodes goes down, so one of your VMs stops working for some reason, whether it's something you did, it's something the VM just crashed, sometimes that happens, we keep an eye on it, and we automatically repair that and replace it. So your node could go down, we'll put a new node in your cluster, and you won't even notice. We have auto upgrade, so you don't have to worry about running updates and stuff like that. You can just click a button, and it will automatically roll you up to the most recent version of GKE. So if any of you guys have ever tried to manage a fleet of your own servers, that is a super time saver. And last but not least, we even have auto scaling. We're going to talk a little bit about pod auto scaling, but this is node auto scaling. So we can actually add additional nodes into your cluster. If your cluster is not big enough to handle the load you're trying to, we can throw in some extra VMs, beef it up for a little while, and then when the load subsides, we can take those VMs back away, and you only have to pay for what you used. OK, so with all that in mind, let's go back to the presentation, or the computer here, and set up a GKE cluster. All right, so I'm going to click right here to create a cluster. It's got a lot of the same stuff. We better just match numbers, right? We don't want to be wrong. OK, so we have a couple of different location types. We can either have our cluster be in a zone, or we can have it be regional. So what happens when we select a region is we no longer can select a zone, but instead it's going to create nodes inside of each different region. Sorry, each different zone. So we're going to have one region, but the nodes are going to be spread throughout the zone. And we can also beef these up a little. Add some CPUs, great. So what's happening here is I selected 1 for number of nodes, but it's per zone. So I'm going to have 3 nodes total, and it's going to be spread out between the zones. OK, and if any of you have ever tried to start up Kubernetes before, this is 100 times faster than I've ever spun it up on my own. So I always love doing this because it's very fast. So while it's spinning up those VMs, we'll go back to the slides a little bit, and then we'll come back and take a look at these in a few minutes. Can we go back to the presentation, please? Great. OK, so let's talk about deploying the application. Let's take a look at the infrastructure. So we have a couple of different components going on here. It's a lot to take in, but let's break it apart. So the first thing we notice is we have the end user. The end user is going to be interacting through a load balancer. The load balancer is going to be distributing all of the traffic between the pods. So we talked about pods earlier. That's an atomical unit. The pods are inside a deployment. So we're going to tell Kubernetes, hey, we have a deployment. The deployment is going to manage the pods for us. The load balancer is going to direct traffic to all of the pods, and the pods are going to connect to our Cloud SQL instance, and our Cloud SQL instance has high availability, so it's got a synchronous replication to a standby instance. If we take a look inside the pods, you can see we have 2 different containers. One's our application, and one's using the Cloud SQL proxy. So this is what we call the sidecar pattern. So let's take a look inside the application container. So this is a file from the actual deployment. You're going to see it in a second when I deploy it. You'll notice we're using secrets. So secrets are a way that Kubernetes can represent information. You create a secret, and it can interject those into the pods as environment variables. This is a really good way to pass along information. So here we're passing in information about the database user and the database password. You can also see, if you look on the top there, we have the container port. So it's listening on 8080. So this is just the default for Flask. And you can see for image, that's going to pull a container image right from my GCR repository. We also have the sidecar. So this is the sidecar that goes in addition to the main car. And you can see this is the Cloud SQL proxy. This is an image we provide, so you don't have to make your own if you don't want to. You can if you want. It's open source. You can just slap this on there. It'll pull it down. And then you're just going to give it the command to start. So we're specifying the instance name, the port we want the proxy to listen to, and then the credential file for the service account. That's all we have to do to get it up and running. We're using volume mounts to pass this secret in. So it's mounting the file as a volume. It's putting that volume into the container, and the container is accessing it when it starts up. So then we talked about the load balancer. The load balancer, all we're going to do is specify a name. It's going to be called tabs versus spaces. We specify a type. The whole thing is called a service. We specify the type of service. The service is a load balancer. And then the selector. The selector is going to determine which pods it's pointing to. So we're going to be using app tabs versus spaces. That says grab all of the pods with the label tabs versus spaces and start using those. And then at the end, we're specifying what port we're listening on. Now, just because my development server listens on 8080 doesn't mean we want to here. So I'm going to listen on port 80. I'm going to send that traffic to my pods, which are listening on port 8080 and with TCP. OK, so now let's walk through deploying the application and take a look at everything. If we can switch back to the presentation, please. So now that we have these up, let's go ahead and take a look at what exactly we have going on. So this is the database that we just created. You can see here that we see CPU utilization. So this is an instance of a database, but we actually have to create the database real quick on here. You can do things like you can manage connections, you can manage users. All of that stuff is provided here. We've got backups, replications, operations, all that stuff. I'm just going to create a real quick database for my application to connect to and use. OK. So that is creating. So now I can come over here and do the same thing with my GKE cluster. I can take a look. You can see the master version. It has an endpoint. So this is the endpoint that I would connect to the cluster itself. We have a whole bunch of other things in here. There's a lot of information that's all in here. You can take a look at any persistent volumes, any nodes. All of that stuff is listed here. What I want to do is connect. So I'm going to go ahead and click connect right here. It's going to give me a URL, and I'm going to take this and move over to Cloud Shell. So if you guys haven't used Cloud Shell before, it's a really cool thing that you get free with a GCP account. Essentially what it is the VM that's, it's not persistent. You keep your home folder, but it launches up with a click of a button. So you can click it and you can open it up. You can see right here I have the application open in the background. I haven't deployed it yet, but just to show you guys the code, it's very small. It's one Python file. It is 175 lines of code, and most of that is comments. So there's not a lot going on there. It's just going to connect to the database for us. And if we put this, OK, so that is the command to connect. We're going to go ahead and click that, and it's going to connect to our cluster. Can everybody read the text OK, even in the back? Good? Awesome. All right. OK, so now I can talk to my cluster. OK. Maybe. OK, no resources sound. That's to be expected. Let's take a look at the services. So we should see at least one, because Kubernetes itself is a service. OK, we've got one, so we're connected to our cluster. Everything's good. So we talked a little bit about secrets. So let's take a look at what the secrets looks like. We just have in here the database name. Now, these are encrypted, but you saw me enter in earlier. It's not very hard. In case you forgot, it's 1, 2, 3, 4, 5. These are just encrypted. You can either create these via the command line, or you can 64-bit encrypt it and throw it in here, and Kubernetes will take care of it automatically. So I'm going to do kubectl create. This is going to tell Kubernetes to create the file, and I want to start with the secrets. OK, so there you go. You can see at the bottom I created 2 different secrets. One is the credential file, and the other one is the secrets for connecting. So that is the database name, password, and username. We can take a look at the deployment. So this is the deployment that we talked about earlier, right? Just to go over it all again, we can see the name. It's going to apply labels to everything in here. This is going to how our load balancer is going to find it later. For containers, we have tabs versus spaces. We have the gcr.io. We have our secrets put in here, so it's going to use those secrets. This is the sidecar, right? So I know it's hard to see because it's not a very big, well, it is a big screen, but it's not very big font. So the only thing we need to do is put the instance connection name in here. So if we come back to our database, we can go to the overview, and the instance connection name is right here. So the cool part of this is I don't even have to worry about, with the proxy, I don't have to worry about if I create a new database, or sorry, if I change the IP address for some reason, like if I'm running private IP and I switch VPCs, the proxy will automatically figure it out and update for me. So I'm going to go ahead and create that right there. Okay, so I'm going to create the deployment. All right, so you can see the deployment is now created. So if we try and find some pods again, we should hopefully see something. Okay, so if we take a look there, we have one pod that started up, so that's our deployment. Our deployment says, hey, I'm supposed to have this application running. It's supposed to have a pod. That pod has 2 different containers in it. So if we look at the status, it says it's container creating. Usually the first time a container creates, it takes a little bit longer because it's got to pull those images from the repo. But we can keep updating this to make sure it's good to go. Okay, well, we give that a second. We're going to go ahead and start talking about the load balancer. So for the load balancer, it's pretty simple, exactly what I had on the screen. We're using a selector, app, tabs versus spaces. So select all the pods with tabs versus spaces, and we're going to listen on port 80, and we're going to send that traffic to port 8080. Okay, and that's all it took to create the load balancer. So it read that file in, it deployed it, everything is good to go. So let's go back and see if our pods are up and running. Okay, you can see the pod is running. It's about a minute old. It has both the containers are up inside, and everything should be hopefully working correctly. We're about to find out for real, though. So while that is creating the load balancer, let's come back in here and look around. So we already showed you what the SQL instance looks like. You have CPU utilization right now, not a lot's going on. We can come over here to the Kubernetes Engine. We can get out of this. So we can see workloads. So right here we have a deployment. We have tabs versus spaces. I can click it and take a look. So far I don't have any CPU, memory, or disk. It hasn't been running long enough, but after a little while we should hopefully start to see that kind of info. Right, perfect. So here we have CPU, memory, disk. So you can actually monitor each application and see what it looks like. We can look down, we see labels. This has labels, app, tabs versus spaces. That's how our load balancer is going to find it. We can see down here, these are revisions. We have managed pods, so these are all the pods. And then we have exposing as a service. So this is actually our load balancer right here. We can look at services too. All right, we have an IP. So let's click it and make sure everything's working. Awesome, our application's up and running. So I'm going to take this IP address. I'm going to bring it over here. Okay, now you guys go ahead, pull out your phones, open up your laptops, whatever you need, go to that IP address, make sure I'm telling you the truth, I'm not pulling any wool over your eyes, and let's see who can win between tabs and spaces. Has everybody got the IP okay? Anybody still waiting? Okay, so just to make sure, let's check on, see how things are going. Okay, it looks like it's a pretty close vote. Spaces is barely pulling ahead. Good news for the tabs folks, I don't check to see if you voted twice, so just start clicking. All right, so let's go ahead and go back to the slide real quick. Okay, so now that we've deployed our application, let's look at some of the things that can go wrong and what we can do to stop that. We've already done a lot just by deploying with Cloud SQL and Kubernetes, but let's look at what else can happen. So when we talk about fault tolerance, it's important to remember it's not fault proof, right? We don't want to try and make sure that nothing can ever go badly ever. That is a losing strategy. You will never be able to make that happen. You're always going to have some type of hardware failure or something that's impossible to schedule around. What you can do is have a backup plan for handling failures so that if something does go wrong, you react quickly and hopefully without a lot of man hours involved. You don't want to focus on eliminating the chance to go down, focus on getting back up as quickly as possible. So let's talk about application failures. Now, this is like 170 lines of Python. I'm not very good at Python, so maybe I did something badly and somebody figures out a way to make it crash. What's going to happen? So Kubernetes is constantly monitoring this. It's going to take a look and say, hey, wait a minute, there's supposed to be a pod running, and it's supposed to have this application in it. I don't see any pods. It's going to start that pod back up within seconds. I can go in, I can kill a pod, Kubernetes is going to bring it right back up. High traffic. So let's say that my little pod wasn't enough to handle all of the 500 plus people in this room. If that were the case, we have a feature we can do. We can add a pod autoscaler. It's going to add more pods as the CPU usage increases. So as more people begin to go ahead and use the application, Kubernetes is going to go, hey, this one pod is not keeping up. I need to throw some more in there. I don't have to do anything. It's automatically going to react. It's going to scale up. It's going to handle that load for me. OK, how about infrastructure failures? So now we've talked about a bunch of things that can go wrong on my end. What happens if an entire zone goes down? What happens if it wipes out? I can't talk to that node anymore. I can't talk to my Cloud SQL instance. Well, we made a bunch of decisions earlier when we decided to deploy regionally that even if a zone goes down, remember the zones are fault tolerant in different ways. So if one zone goes down, the others are still remaining. So our Cloud SQL instance is going to fail over. We're going to see it go down for maybe a minute, and it's going to come back up. And our Kubernetes instance is going to do the same thing. It's going to look in the cluster and go, whoa, 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 hold on a second. There's supposed to be a bunch of pods running. I don't see anything. We need to fix that. Again, hands off. I don't have to do anything. So with that in mind, let's take a second and examine the fault tolerance. Actually, let's look at the vote real quick and see. OK, somebody has automated tabs, and as you can clearly see, Spaces is not going to catch up anytime soon. All right. OK, so if we look, we've got 2 pods running. That pod seems to be doing OK so far, but we have this load balancer here. So what exactly is this load balancer going to do? It's pretty simple. It's going to apply to all the labels where tabs versus spaces is. So it's going to look at all the pods with tabs versus spaces. Oh, that's the load balancer. I want the autoscaler, sorry. Autoscaler. So this is horizontal pod autoscaler. We have min replicas right here. So min replica says, hey, I want at least 2 pods running all the time. So what that means is that even if something goes wrong in that pod, there may be like a split second where Kubernetes doesn't realize that pod is down. But as long as I have 2, even if something goes wrong in one, the other one is still up and running. So even if we're waiting a couple seconds for a new pod to come up and replace it, I have that one at least responding to requests. I can also set a max, right? So I want to make sure I don't run too many pods. If I only have 3 nodes, too many pods isn't going to help me out either. It's going to add a lot of overhead. So I want to limit that to 10. So only have 10 pods. Anywhere between 2 and 10 is perfect. We can also look at the target CPU utilization. So this is how Kubernetes is deciding to scale. This is a metric that you can create your own metrics. Kubernetes is really extensible. This essentially says, hey, I want each pod to be at about 50% load. That's going to give me a little leeway just in case the pod spikes up in traffic. It's going to go, hey, this pod's way over 50%. I'm going to throw some more pods in there to balance it out. And then we just have some API stuff right at the bottom that you don't really have to worry about. So with that in mind, let's deploy my auto balancer, or my autoscaler. OK, so now it's creating my autoscaler. It takes a little bit to start up. I can check the status of it with HPA. So this shows my HPA is the horizontal pod autoscaler. It's going to show its status right here. Right now, I'm unknown out of 50%, so it's still trying to initialize, get some things, see what's going on. We see min pods 2, max pods 10. So let's look and see if our pods have changed. I still only have 1 pod, so the HPA is taking its sweet time. I see replicas 1. OK, sweet. So now it started up a second pod. It's only 8 seconds old, so it's still getting there. But we've got our backup pod in case something goes wrong. So even if I were to crash one of these, yes. Is that better? Is it still big enough for everybody to read? Oh, I see. Sorry, I totally misunderstood. Is that better? All right. Thank you, thank you, thank you. I'll be here all day. Okay, so I deleted that pod, and now you can't really notice because I took too long to figure out what you guys were trying to tell me. But so it's hard to tell, but this pod was with the B6MV8, and that pod is no longer here. So let me do this one more time. So if anybody's still trying to vote, which I'm sure the guy who automated that tab script is, he's probably not seeing any dropped connections. Maybe one or two if he's unlucky, but as soon as that pod gets dropped, Kubernetes realizes it, it stops directing traffic to it and sends it the other way. So if I go right back, okay, I got 2 pods, one's only 16 seconds old, so the one that I killed has already been replaced. So let's check again. All right, tabs is really winning. Somebody on Spaces is trying to keep up, but tabs must just be better at automating the votes. So, okay, so we also have that autoscaler, so let me start up some traffic. So I've created a compute instance here. I'm going to grab my IP address, if I can find it. I'm going to grab the IP address. And you guys are just not quite enough load, so let's see what happened if we had several thousand people trying to log into this all at once. Okay, so what this is doing is it's just sending a ton of requests. It's using a tester called Hey. It's written in Go. It's just sending a ton of requests, trying to max out that as much as possible. And we can even come in here and monitor it. So we can take a look at our service, tabs versus spaces. So you can see right now there's a sharp upcrease in CPU usage. That's because we're sending it a lot more traffic than we were. But so far, we still just have the 2 pods. So, okay, so while that's going, we're also going to talk about the database failover. So it's going to take like maybe 30 or 40 seconds for Kubernetes to figure out that it needs more pods. The autoscaler is customizable. We're just using the default options right now, so it plays a little on the safe side. We're going to switch the database. And there's a button right here for failover. So this is really useful if you want to test how your application works. You can click failover. It's going to simulate that failover process. So it's essentially going to crash your database intentionally. Your data will be fine, but it will allow your application to practice failing over. So we're going to click failover. It wants to make sure I'm really this crazy. OK, great. So now the application is failing, and it's down. So if I take a look, it's not working, right? Sorry, the application is working, but it's getting an error because it can't connect to the database. So whoever is voting, your script just crashed. And it's going to be down for a little bit. It's going to take like 30 or 40 seconds. And while we're waiting for that to react, let's go ahead in here and really screw it up. I'm going to delete all of the pods. So unfortunately, I don't have the power to bring a zone down all on my own. But I'm going to delete all the pods because it's a similar situation, right? I've already shown you that I can delete a pod, and it's going to come right back up. Maybe. OK, perfect. So now it's deleting all the pods. You can actually see it deleted 4 pods. So the autoscaler was working hard. It kicked up some extra pods, and now it's deleted those. So if I take a look inside Kubernetes, if I refresh this, OK, you see here I actually caught one of the pods that's in the process of being switched out. So we have 4 healthy pods that have already replaced the 4 that broke, and we have 1 that's crashed and running. And hopefully, if we take a look over here, my database is back up, and so is my application. So you guys were watching me. I wasn't doing anything. Kubernetes took care of that all on its own with a little help from Cloud SQL on the back end. Can we go back to the presentation? So that is examining fault tolerance. We have about 15 minutes left, so I'm going to do some questions at the end here. If you guys are interested in trying this yourself, We have a code lab that's available online. All the code for a similar application, you can create your own meme generator. If the only thing that's different between tabs versus spaces, it's making memes. So you can go to this link right here, github.com/Google Cloud Platform/gmemegen. It's a hands-on, step-by-step tutorial. It does exactly what I just did now, so you can go home and try it out yourself.